In this video, we're going to talk about forms of corrosion. I'll first love to give credit to Prof. Andrews in the Department of Materials Engineering. So when we talk about forms of corrosion, it can be in several ways, which is in two ways, which have the localized and the uniform. So for the purpose of this video, we are going to concentrate on uniform corrosion, galvanic corrosion, and pitting corrosion. Now, when we talk about forms of corrosion, which we can see in stainless steel, we have pitting corrosion, which is a localized corrosion. We have crevice corrosion, which forms in crevices. We have the general corrosion, which can be the uniform corrosion. We have the stress corrosion cracking, which is as a result of what? Mechanical stress to the material. We have the intergranular corrosion, which happens in the grain boundaries, along the grain boundaries of the material. And we have the galvanic corrosion, which happens due to the change in potential of the material in an electrolyte. So we have forms of corrosion which have been categorized into uniform corrosion and localized corrosion. And under localized corrosion, we have the macroscopic, which you can see with your eye, and the microscopic. With that, you cannot see with your naked eye. You need a microscope. So under the macroscopic corrosion, we have the galvanic corrosion, we have the erosion corrosion, we have the crevice corrosion, we have the pitting corrosion, we have the exploration corrosion, we have the dealloying. And for the micro, we have intergranular corrosion, stress corrosion cracking, and corrosion fatigue. These are all forms of corrosion which falls under localized corrosion. So let's take uniform corrosion. And when we talk about uniform corrosion, it's a uniform attack over the entire surface of the material. So if you can see these pictures, the corrosion happens on entire surface of the material, and it's often left behind a scale or deposit. You can see that we have a scale deposit on the material. You can see this brown thing, and it is uniform throughout the material. And we can have some example of this. And this example, we can see some in corrosion of what? Steel roof. We have corrosion of steel roof. We have rusting of cars. We also have tarnishing of silverware, and etc. And let's note that with this type of corrosion, similar level of corrosion all around. So there's similar level of corrosion all around. So if you can see this, it's uniform. Wherever you know that it's uniformly arranged, right? It occurs in uniform. That's what it meant by uniform corrosion. Now let's look at some control of uniform corrosion. How can we control uniform corrosion? So control measures. First, we are going to talk about is the CP system, which is the cathodic protection. The cathodic protection system, whereby we can use the principle of sacrificial anode to protect the material. And we have the impressed current cathodic protection. So under cathodic protection, we have the sacrificial anode and the impressed current. Yes, you are in this video, you get to understand the cathodic protection and this impressed current cathodic protection under corrosion control. We also have painting, right? Painting or coating the surface of the material. And let's note something. Prevent factors of uniform corrosion depends on these things. We have the first I'm going to talk about is temperature. So you're trying to prevent this corrosion, you need to check in these factors. Temperature, we have the velocity, we have the salt, salt, oxygen concentration, and we have conductivity of the material. So before you can use prevent this type of corrosion, you need to have this in mind. Let's look at the next type of corrosion, which is galvanic corrosion. When you see this picture, what comes to your mind? There are two materials here. One is undergoing dissolution, is the same as corrosion, and one is going under deposition. It's not corroding. What is wrong? This is galvanic corrosion, and this happens due to the similar metals in contact with an electrolyte, and when they are in contact with an electrolyte, it brings about difference in potentials. The difference in potentials of the metals leads to corrosion. So this is metal A and this is metal B. But we can see that metal A is undergoing dissolution and metal B is not corroding. What is wrong? This is the reason. The more active metal, which is anode, corrodes. So this is an active metal, which is the anode. So the one which is corroding is the anode because it's more active. And the more noble metal, which is called the cathode. So this is anode, and this is called, the B is called cathode. So the cathode is noble and that is protected. Let's look at something here. The rate of galvanic attack depends on relative anode to cathode surface ratio or areas that are exposed to the electrolyte. The rate is related directly to the cathode anode ratio. So let's look at something. When you are coupling these two materials together, or two metals together, the size of the anode and the cathode is necessary for the galvanic corrosion to happen. Because let me explain in this way. When the cathode, when the cathode is more, or the cathode area is larger than the anode area, what do you think will happen? Now, what happened? The cathode will be able to accumulate more electrons from the anode. What I'm saying that means that the cathodic reaction is, let's take iron undergoing dissolution, we have 2 plus what? 2 electron. So whenever the cathode release electron is undergoing dissolution, and since whenever the anode is releasing electron, it undergoes dissolution, and since the cathode is very large, it can accumulate more electrons from the anode. And when more electrons are being accumulated to the cathode, the anode undergo dissolution. Let's note that. This is very practical. And in different senses, when the cathode is more larger than the anode, what do you think will happen? Now, the anode will give more electron to the cathode, but in this case, it will get to a time that the cathode cannot accumulate more electron from the anode. Therefore, corrosion rate will be reduced. So that is very crucial when it comes to galvanic corrosion. Now let's look at the galvanic series in seawater. These are all based on galvanic corrosive table. Let me explain the table for you. So the table moving up means that it's more active, which is noble, and coming down is more let me explain the simple galvanic corrosion table. You moving up, it means that you are becoming more active, and that is what? Anode. And when coming down here, you become more noble, which is what? Cathode, protected. So let's take a material like, we are taking zinc and we are then coupling it with stainless steel 304. What do you think it will happen? Now let's see something. Since the zinc is more active, in ideal sense, the zinc will undergo dissolution and the stainless steel will be protected. The reason why I say in ideal sense, because there are some conditions. If the size of the cathode and anode is not as wanted, then it gets to a time that one can undergo dissolution and one can be protected. So it can either increase or reduce due to the size of the anode and cathode. So in this case, when you couple this and this, it means that the zinc is going to protect the stainless steel. The same thing when you couple nickel to bronze. From the table, you know that nickel will undergo dissolution and bronze will be protected, since nickel is more active than the bronze. Let's look at something about the table. This gives no indication of the corrosion rate. What it does is that it can tell you that corrosion is going to happen, it's happening, but it doesn't tell you the rate at which it will happen, maybe in milliliters per year or MDD, that's milligram per decimeter per day. So that doesn't show you the rate at which the corrosion is going to happen. And useful predicting galvanic relationship. Yes, because it can even help you to know that this, when you couple this material to this material, which one is going to undergo dissolution and which one is undergoing what deposition. And the series depends on the environment, as stated here. This, we are talking about what? Sea water. So under different environment, the series will change. Now let's look at factors, right, that affect galvanic corrosion. Now we have the environmental factors. And the environmental factors can be like salt, moisture, and temperature. The reason why temperature is a key here, very important when it comes to galvanic corrosion. That is the factors. Now let's look at something here. Metals with less resistance to a given environment becomes anodic, right? And it means that it's more active when you couple a metal, two metals together, and the metal is more active. It becomes an anodic member, right? But let's look at something. Let's take an example, which is zinc hydroxide, right? And with zinc hydroxide, it is stable to a certain temperature. So this metal here, or this member, is anodic. It's an anode, right? At a temperature of 60 degrees. It's anode at a temperature of this. But when the temperature increases from 60 degrees, it forms zinc oxide, which therefore becomes a cathode. So when it is greater than 60 degrees, it forms cathode. So that's why I say that the environmental effect is very important, because you would think that a metal is anodic, but at certain temperature, the metal will become cathodic, whereby let's assume that you are coupling this with iron at temperature of 60 degrees. You know that the zinc will undergo dissolution and the iron will be protected. But at a temperature which is greater than 60 degrees, you will see that the zinc will be now protected, whereby the iron which you want to protect will undergo dissolution, and that's very not encouraging. Let's look at the distance effect. So we have, you know that corrosion happens at a junction. So this is a material A and this is a material B. Let me do a material B. Corrosion will initiate at a junction here. It will initiate at the junction. So what it means is that this is material B. When far away from the junction, when you are moving far away from the junction, the corrosion rate will reduce. But when you are close to the junction, corrosion rate will increase, because corrosion initiates at the junction when two materials come together. For galvanic corrosion to happen, when two materials come together in the presence of electrolyte, then due to the potentials, then corrosion starts to set in. Are you getting the difference in potentials? Because they are coupled together. But if you are far away, then corrosion rate will reduce. Now let's look at the area effect. The area effect is, let's take a diagram A. This is diagram A. We have this diagram. This is A, and diagram B have this. This is diagram B. Now this is the cathode, and this is the anode. And here this is the anode, and this is. Which one do you think it will undergo dissolution? Let's analyze this. For figure A, this is the cathode and this is the anode. That means that the anode is very larger than the cathode. So you know that the electrons move from the anode to the cathode. So when the electrons are moving from the anode to the anode undergo dissolution. In this case, the cathode is too small to the extent that when it can accumulate a lot more electrons, and to a certain state, the cathode will not be able to accumulate more electrons again. Therefore, the corrosion rate will be what? Reduced, because the cathode will not be able to accumulate more electrons. So at a small cathode and a larger anode, the corrosion rate will reduce. Similar to B, we have a big cathode and a small anode. That means that electron move from the anode to the cathode, electron move from the anode to the cathode. And since the cathode is bigger, it will be able to accumulate more electrons. And when electrons are accumulated, dissolution happens, greater dissolution. Therefore, the corrosion rate of this figure will increase. That is the area effect. So whenever you are doing some engineering material, you need to know the anode to cathode ratio that you use. Always the cathode should be lesser than the anode. Always the cathode should be smaller than the anode, and which in that case corrosion rate will be reduced. Let's look at some beneficial application. We have the cathodic protection, which is sacrificial protection, and this is the anode whereby you have the anode and the cathode, and then you want the anode to dissolute or to undergo dissolution and protect the cathode that you want, right? You also have the galvanizing, whereby you use zinc to protect steel, because on the galvanic series in seawater, zinc is more reactive than steel. So that means that zinc can protect what steel, but as a condition for the environmental factor, also come in with temperature, because at certain temperatures, the anodic member can change to cathode. Okay? And also we have battery, which chemical to electrical energy. We have cleansing wire. Now let's look at some control of galvanic corrosion. What will be the first control of galvanic corrosion? That is using which you, if coupling of the similar metals is necessary. If you look at the galvanic series, when you choose series which are very close to each other, the corrosion rate will reduce. So we should choose metals close together in the galvanic series. When you choose metal close together in the galvanic series, it's going to reduce the corrosion. The second one is the area effect, right? So avoid unfavorable anode to cathode surface area ratio. Use an anode area as large as possible. So in this case, what it means is that the anode to cathode ratio, you also check that. The anode to cathode ratio, you will check that. And this is the anode to cathode ratio. This is the area. And the third one is you are going to use chemical, that's electrically insulation. If you use insulation, you insulate one of the material or two of them, the cathode or anode, which prevents what the rate of corrosion. The fourth one is anodizing valves. Anodizing is intentionally introducing passivation layer on the material to prevent further deterioration of the material. So if you have brought a passivation layer on it, that means that the content will not be there, because there's a passivation layer which protects the material from dissolution, right? Yes. Let's look at pitting corrosion. Now, when you talk about pit, you know, pit is a hole, pit. Right? So pitting corrosion is a localized corrosion attack forming small pits or holes. As you can see, we have small holes. This is very, right, yeah, look like what, a butterfly. And this, we have these small holes, and this hole look like lava. Lava one thing. So we know that it's oxidation occurs within the pit itself. And when I talk about oxidation, it's another reaction, right? Oxidation, that means that the metal will undergo dissolution, Mn plus what? N electron, right? Oxidation happens within the pit itself. Complementary reduction at the surface, and hence in stagnant conditions. So in stagnant conditions, it improved, right? Now, pitting corrosion is one of the most dangerous or one of the most damaging form of corrosion, because you sometimes you never even know that it's undergoing pitting corrosion, and then it will eat inside. It's going to destroy inside of the material, and you'll be there, and then just happen, and then people will die. A pit may be what initiated by a localized surface defect, such as scratch or slight variation in what composition. Even painting, when you are doing coating and you leave some holidays in the coating, those holidays can initiate pitting corrosion, and that will be very this one. And note that the pitting corrosion, the size of it is very different. You can see that they have this slab, have two eyes, we have this, we have the narrow and deep, we have the epilepta, we have the wide and shallow, we have subsurface, you can see subsurface, we have undercuts, and we have vertical and horizontal. As this, these are all examples of them, and then see the example. So now let's look at some causes of pitting. What causes pitting corrosion? So I'm going to use this to explain what to cause pitting corrosion. So this is the stainless steel, and we have a protective layer here, right? So let me do in Russia, and this is protected. And what will happen? Chlorides damage passive film. So chloride will, because it's influenced into sodium chloride, which is the salt area, right? The chloride is very stubborn. Then they try to what? Destroy the passivation layer. And when they destroy the passivation layer, initiating pitting and breaks of oxide. So when it breaks off, like you see this side, they break the oxide and then go inside, right? And what happened? The localized production of positive metal ions in the pit attract the negative chloride. So you know it's positive, and it's positive metals or positive ions always want negative ions. So then they try to attract the what? The chlorine in the salt. They attract them. They are attracted. And when they are attracted, what they do? They form what? And once they are attracted, why are they attracted? So that they can neutralize the charges, right? Yes. So when they attract them, they form what? Metal chlorides, which hydrolyze with water to produce the corresponding metal hydroxide. So when they hydrolyze with water, then they form rust. This form metal hydroxide, and this accelerates corrosion process. The chloride ion accelerates because they break the passive film, right? That's how it happens. You understand? Yeah. Let's look at some control of heating corrosion. And the first control is one, proper selection of material. So proper selection of material. And the material should be free from any cracks, scratch, or any initiating that will bring out heating corrosion. And we also need to control pH. The pH need to control. You need to control the pH. You need to control the chloride. You know that chloride brings the passive films, and also the temperature, right? The third one I'm going to talk about is cathodic and anodic protection. Cathodic and anodic protection. And we have the fourth one, which we are going to talk about, the use of high alloys for what? Increase resistance to heating corrosion. So you use type 315 or 316 SS instead of 304 SS stainless steel. So you use 316 stainless steel and 304 stainless steel. We also have others which you can do coating. We have the zinc sulfate prim. We also have the zinc spraying metallizing. We have the chemical coating, that is dip coating, spray or spin coating. We have hot dipping, that is steel galvanizing. And when you do that, I think it's going to prevent or control the heating corrosion. Thank you very much. This is the end of lecture 2.